right, so this is lesson 7-8. We're going to talk about simple interest, so hopefully it's pretty simple. Many real-world phenomena can be modeled by functions that describe how things grow or decay as time passes. For example, such include populations, bacteria, AIDS virus, radioactive substances, electricity, temperatures, credit card payments, just to mention a few. So very important with some great real-world examples for you to see. So this first kind of exponential function we're going to look at is often referred to as simple interest functions. So some examples would be a fixed amount over time. So Aesop's fable of the golden goose. Each day the golden goose lays a single golden egg. The goose couldn't lay faster, and the eggs didn't grow into golden geese of their own. So that's that fixed amount. Corporate bonds, so a bond's with a face value of $1,000 and a 5% interest rate pays you $50 per year until it expires. You cannot increase the face value, so that $50 is all you will get from the bond each and every year. So simple interest is the most basic type of return. Deposits $100 into account, let's say, with a 50% annual interest. Would look like this. So here from 0 to 1 year, so you've got that $100, you would make $50. The next year, you'd earn another $50. And the third year, you'd earn another $50. So that's never going to go up. That's why it's that simple interest. So that's that green money that can't grow. So that simple interest is the $50 that just sits there. So simple interest has a simple formula. It's you earn A times B. So the initial amount or the investment times the growth or decay rate. So it's A times B to the whatever power, so that initial A times your growth or decay. So here's kind of our formulas that we're going to be using for these simple interests, depending upon if we're growing or if we're decaying. So A greater than 0, so that's your starting amount or initial amount. 1 plus your R, your rate. So are you growing or decaying? If you're growing, you're going to use a plus. Add that rate. And that rate does need to be in decimal form, not percent form. And then your second part, or third part here would be your T, your time. So when it comes to decaying, you're going to have subtraction. That's the only difference. A is your initial, R is still your rate as a decimal, T is still your time. It's just subtracting that rate because you are decaying. So let's talk about how do we know if we're growing or decaying. And we're going to try an activity in class to kind of practice this with the sorting. So for this first part, we look at our rate. Is it greater than 1? So is it growing, or is it less than 1 but greater than 0? Is it between 0 and 1? So we kind of break that fraction down as a decimal to see. So this would be 0.75, and that is less than 1. So that means that we are decaying. Here, 1.05, we're greater than 1, so we can definitely see that is going to be a growth. So try those last two on your own. Pause, check when you're ready. All right, so number 3 is decay, because that is less than 1. And then number 4 is a little tricky. Hopefully you didn't see that fraction and think it was decay, because really 5 halves is 2.5, which is greater than 1, so that should be a growth. All right, so understanding exponential growth. Let's start by looking at the basic system that doubles after the amount of time. For example, bacteria, we can split, and it doubles every 24 hours. So we can get twice as many noodles when we fold them in half. Your money doubles every year if you get 100% return. Lucky. So here's what that would look like. So starting out here, so then it's doubling. Well, then it's doubling with your new, and then it's doubling each time that you add that new kind of in there. So splitting into 2 or doubling is very common progression. Mathematically, if we have x and it splits, then we get 2 to the x, or 2 times that. So 1 split, we'd have 2 to the first, or 2 times as much. 4, we'd have 2 to the fourth, or 16 times as much. So that growth of 2 times is 2 to the x. So said another way, doubling is 100% of the growth. So we can rewrite our formula like this. Growth equals 1 plus 100% to the x power. It's the same equation we just separate 2 into what really is originally your original value. So 1 plus the 100%. So there's your 2. Of course, we can substitute any numbers, 50%, 25%, 200, for the 100 and get that formula for the new rate of return. Okay, so I kind of have this from the front just so that you can see those values from the front page as we're working on some examples together. So y is going to kind of be your total. A, remember, is your initial, R is your rate as a decimal, and T is your time. So let's go ahead and plug in. We've got our initial amount for our house. Appreciation is good. That means you're making money. Depreciation means you would lose money. So this is going to be 0.06, and then we have our T for time, 10 years. So when we go to plug this in, we have our initial times our 1 plus, because it is appreciating, making money, growing. Excuse me. And then we have it to the 10 power. So you're going to type this into your calculator, making sure that you've got those parentheses, because those are important. And you're making sure that it's to the 10th power. And we get our total, 232812020. So that is $232,810.20 after 10 years of appreciating at 6%. So go ahead and try the next one. This is a decay example, so that means we are decaying, which means in your formula, make sure you're using subtraction. So plug in your starting amount, your rate, make sure it's as a decimal, that percent, and then be careful on this one because you're talking about each month and then half a year. So your time is going to be however many months would be in half of a year. So try that, check when you're ready. All right, so let's go ahead and check your answer. Should have had 821 times 1 minus 0.15 to the 6th power, 6 being 6 months, which is half of a year, because we're counting by each month. And then your answer is 309.6, but really we don't need that 0.6 because there's not 0.6 of a fish. So it would be 309 fish if it is decaying at that rate. All right, let's go ahead and take a look at some trickier examples here. So we've got super deadly strain of bacteria causing this zombie population to double every day. So doubling means we're growing. So there are currently 25, so that's our start. How many days? Well, we don't know our time is what it looks like, but we do know at the end, this is how many zombies we have, and we're doubling. So that means we're going to be 100% increase. So when we type this in, or put this in to our formula, it is our starting point, parenthesis 1 plus, because we're growing, 1, or 1.0, and then to the x power. So we have 25 times 2 to the x power, and we're going to go ahead and work backwards on this one. So divide by 25, and let's see what we get there. We get 1,024 equals 2 to the x power. So we're looking for our exponent here. So this is where those logs have come in to play. So to figure out that exponent, it's log base 2 of 1,024 equals x. So this is when you can use your change of base formula and do log 1,024 over log base 2 in your calculator to figure out what that exponent is going to be, or how much time. So dividing that in your calculator is going to get you 10. So 10 is our time, 10 days. Uh-oh, it's pretty quick. All right, try this last one on your own and then check when you're ready. All right, so Lindsay Lohan starting out at a 0.18, and according to this, she would decrease at 1.5%, so we do have to change that to a decimal, 0.015. So we're going to subtract, since it's a decrease or depreciation kind of to the fourth power for 4 hours, and we multiply and we get 0.169, which I rounded to a 0.17. So not much less than she was starting out.